Hello. So in this tutorial, we're going to revisit some of our old chestnuts of objects rolling down inclines, but from a different standpoint. Rather than using the second law of motion and kinematics, we're going to use an easier approach, and that, of course, is conservation of energy. So the focus on this is rotational kinetic energy, something I alluded to last week, 2 weeks ago, when we talked about a marble rolling down a ramp and how its velocity at the bottom cannot be easily calculated, or cannot be simply calculated just by doing UG equals KE, because there's rotational kinetic energy. So we're now going to learn how to solve that. It's not too difficult a problem. You just got to realize that at the bottom it's going to have two forms of kinetic energy, and they're simply related to one another. So let's review. If you go back to the previous note sheet where we did angular dynamics and we had a solid sphere rolling down, we found that the acceleration, when we did all the analysis, which was a bit of a pain, was a fraction of g. It was 5/7 g sine theta. Okay? And then if we wanted to find the final speed at the bottom, all right, which we didn't necessarily solve then, we would say, all right, we know some distance d that it's traveling, so its final speed at the bottom is going to be the square root of twice the acceleration times d, right? That just comes from v squared equals v naught squared plus 2ad. All right, so if we substitute that in, our acceleration based on torque and angular acceleration, etc., we find that that value becomes radical 2 times 5/7 g sine theta d. Okay, so simplify that a little bit and we get 10/7 g sine theta. All right, now I'm making it look pretty simple here, but there is the kinematics part. We've already done all the forces and angular accelerations, so this is a bit of a pain to come to. So we're going to show you an easier way to get the same answer. Okay, so let's do conservation of energy. So we know at the top it has gravitational potential, which is going to be equal to mgh in this particular setup. And at the bottom, it's going to be converted to kinetic energy. I'm going to put, sorry, that's an E. T for translational, that's the forward kinetic energy that we're familiar with, and then a kinetic energy R for rotational. Okay, so really all that we have to do is how do we calculate the rotational kinetic energy? Well, let's pretend as the marble is here, right? It's moving forward with a V. So we know at the very least that there is a kinetic energy that's 1/2 mv squared. All right, so that's not quite rotational. We're going to use this to get rotational. Well, we know that as it's moving forward with a velocity v, it's rotated to its angular velocity by a simple relationship of v is omega r. Okay, again, where r is the radius of the sphere. So if I substitute that into v, I get 1/2 m omega squared r squared, right? If I square that, which I can rearrange to say 1/2 m r squared, right, times omega squared. Well, I want you to recognize the mr squared. That's nothing more than the rotational inertia of the object. That's the definition of rotational inertia. So that's I. So long story short, we can calculate rotational kinetic energy as 1/2 I omega squared. Okay, so it's kind of like 1/2 m. Instead of m we have I, and v, instead of v we have omega. So it shouldn't be too surprising to us. And remember, omega is v over r. Okay, so now let's put this together. Okay, so at the top we have UG, at the bottom we have translational and rotational. Okay, so this is mgh equals 1/2 mv squared plus 1/2 I omega squared. Now the I omega squared is a generic equation. It could be any moment of inertia. Since we're dealing with the sphere, we know what its specific I is. So let's say I of a sphere, we learned before, is 2/5 mr squared. So let's substitute that in. And we know that omega is v over r. So we're going to substitute that in as well, all in one step right there. So I'm not going to, I'll rewrite this. So we have 1/2 mv squared plus 1/2, all right, I is 2/5 mr squared times omega is v over r quantity squared. All right, looks like a pain, but it's not too bad. So I see I have a v squared over r squared. So the r squareds cancel out. That's nice. And right here becomes 1/5. So let me run out of space here. I have mgh, now that's still over there, is 1/2 mv squared plus 1/5 times mv squared. Okay, so I still have the mgh here. The m's cancel, not a surprise, it shouldn't matter. If I add these two v squared terms, I get common denominator would be 10, so this would be 2/10, this would be 5/10, this would be 2/10, so I get 7/10 v squared. And if I solve for v, okay, I'm running out of space here, I bring the 7/10 over the other side, I got 10/7 times gh. Take the square root of that, and there is my answer. And if we look up here, we see sure enough there is our 10/7, whoop, that's g sine theta d. Oh yeah, radical 10/7 gh, because h is nothing more than d sine theta. Okay, so it turns out I think that's a lot easier to do. Okay, and note that the velocity doesn't depend on the mass. And maybe less, and that's not surprising, what may be surprising is it doesn't depend on the radius. So it doesn't matter whether I roll a solid marble or a solid softball or lacrosse ball or any solid sphere, it will have the same speed if friction is more or less the same. But instead it depends on little g, okay, and of course the height that it falls. Now, if we want to apply this to a hoop, how would things change? Well, it wouldn't change too much. All that we would change is the moment of inertia. So if we have a hoop, if you look that up back in your notes, the I of a hoop is equal to mr squared. It's pretty large, okay, because there's so much of the mass is along the radius. Whereas, again, a sphere is 2/5 that. So if we do the setup, right, we have mgh once again, and I'm not going to go through this all, okay, equals 1/2 mv squared plus, right, 1/2 I is mr squared times v over r squared. That's our v squared. That's our omega squared part. R squareds cancel out, and this term is just 1/2 mv squared. Add it together, and I've got mv squared. Well, this one's pretty easy algebraically. So this becomes v equals radical gh. And we notice that that is less than radical 10/7 gh that we got for a sphere. Okay, so there will be problems in the homework that test this. And there's one last thing we want to look at. And here's another example, okay? So I've got some turntable here looking from above now. It's going around and around because there's some force acting along its outer edge. Okay, and we can ask if the force acts over one revolution. Okay, so as it spins, the forces keep there. What will be the angular velocity? Okay, well, we're given one revolution, we want to recognize is theta. Okay, we're given an r, we're given an f, and we want an omega. So we could take a torque, F times R, angular acceleration, and find angular velocity. Or we could, again, use the idea of energy, or in this case, work. Okay, so we could use the work done to create a change in rotational kinetic energy. Right? Where rotational work is analogous to linear work. There's really no difference between them. Linear work is a force times distance, so the analog would be a torque times an angular distance. All right, I'm going to show you off to the side here why they're the same thing. A torque is an F times an R, whereas theta is some distance, I'll call it delta x, over R, and sure enough we get F times delta x. So there's essentially the same thing, but just written differently in terms of the rotational aspects. Okay, so now we're going to apply our equation. Remember, we're looking for omega. So we can say that the work done right, goes towards a change in kinetic energy, in this case rotational. So that's tau omega is going to equal a change 1/2 I omega squared, okay, since we're interested in that. Now, if we look up the I of a disk, right, that's mr squared, once again, I'm sorry, I take that back, mr squared over 2. Okay, so it should be less than that of a hoop. So we have, and torque is F times R. So we can say, I just want to make sure we have everything here right. We can say F R times theta, right? Theta is going to be 1 revolution, is going to equal 1/2 mr squared all over 2 times omega squared. Okay, we're solving for omega, right? We see that, let's see, this becomes 1/4. Now I'll work it out. So I have omega equals square root, okay, 4 times F. I'm going to have R over R squared, so there's over an R, and times theta. Okay, I think I've done that right. And then for 1 revolution, I'd put in, this becomes 1 revolution is 2 pi radians. So I would have that. So someone check my work, make sure I didn't do something silly there. I have a feeling that I did. So it doesn't remind me of something I was doing earlier, but I don't know. All right, lastly. Okay, I have a generic graph below, all right, of rotational kinetic energy as a function of angle. Okay, and I want to know what the graph represents, the slope of the graph represents. Okay, so we can work that out. So at first blush, it looks like just Ke over theta, which we probably don't recognize. However, we can equate the total kinetic energy gain as work done, right? Work over theta. And now that we should make a connection from this, right? We learned earlier that torque times theta is work, so therefore the ratio of work to theta is nothing more than the torque. So you want to be able to interpret graphs like that. You've done many things like that before with force distance and all things, so it's nothing different with rotational. Okay, so we'll see more problems like this on the homework. And the key thing to remember is if you're talking about a change in height and something's rotating, you have to consider angular kinetic energy as well as linear kinetic energy if it's moving forward.